Good afternoon once again. So in today's looking at an introduction to computing, to computer systems, essentially. So last week, we basically introduced the module as a whole. So we introduced the module discussing the various topics that we were going to be looking at. Now we're going to start with the first and fundamental topic of understanding the basis of computers. Although we did a few definitions last time, we will be diving a little bit deeper into this. We will also be looking at the reasons or the importance of studying general computer architecture and understanding all the bits and pieces and how they kind of fit in together and operate. So every set of slides you have, and I will be sharing these slides. For example, the slides that I have here have already been uploaded, so you can download them after the session. Every set of slides will contain a section with an outline of what is going to be discussed, and also a section called the learning outcomes section. And this learning outcome section is the most important bit. It shows you for an examination, any question coming out on this topic will be focused on this. So we will be covering something like 7 different topics, 7 different chapters. And the exam, or rather the test, the 2 tests that we're going to be having is going to encompass all these 7 or so topics. So for this particular chapter that we're looking at, these are the questions that we will need to be able to answer in order to be able to deal with the exam appropriately. So it says you need to be able to describe the basic building blocks of a computer system. That means you need to understand the general architecture of computers. The second says identify the different types of computer systems, indicating that there are types, and those types are classified based on their characteristics. So we'll look at a few characteristics of different types of systems. And of course, describe the different protocols and standards in a computer system. So what is the meaning of the term protocol? What is the meaning of the term standard? And what are some examples of it? All of this we will be taking a look at today. So with that said, let's go ahead and begin. Here are a couple of key terms that you will be eventually familiar with after the end of this topic. There are a lot. Most of them you already know. A few of them we will be touching on bit by bit. So first and foremost, let's ask the question, why do we need to understand general computer architecture? As Bachelor of Science in any field of technology, which is what all of you are studying, you're going to be graduating with a degree called a Bachelor of Science. Some of you in software engineering, computer science, IT, and so on and so forth. It typically means that you will be an expert in be able to diagnose real world problems that can be solved with IT. So the computer is a tool that we use to solve problems in the real world. So your job will be to be able to identify the types of problems that can be solved using computer technology. So to begin, here's an example of a typical computer advertisement. So here you can see this is from the Apple website, and it's describing a particular system. So what's interesting and what should be notable to you as an IT person is, what do these terms actually mean? The companies that build these computers give what we call a specification sheet. This specification sheet describes the capability of the computer. And the reason why this is very important is when you're buying a tool, you need to understand how to use the tool or what are the capabilities of the tool to know that if it can solve your problem or not. So depending on what you're looking for, the specification will help guide you as to the capabilities of this system. So the first example over here says that this is an 8-core CPU with 10-core GPU, 8 gigabytes of unified memory, and 512 gigabytes of SSD storage. So what do these things actually mean? So just to give you a general outlook, let's start with the first term, 8-core CPU. The term CPU stands for Central Processing Unit. The term central indicates that inside a computer, there's more than one type of processor. So for example, your GPU, Graphical Processing Unit, is a type of processor. You also have a sound card, which is a processor for generating sound. You also have something called a network interface card, NIC. That network interface card is a component that consists of your Wi-Fi, Bluetooth adapter, as well as your Ethernet port if you have an Ethernet port on your device. So that's the network card, the network interface card. It's also a type of processor. So there are several components that are capable of processing specific type of data inside a computer. So the term 8-core CPU is not talking about those general processors. It's talking about the central processor. The job of the central processor is to control and coordinate every single component in that computer. You can imagine the central processing unit like the central command center. I don't want to use the term brain because the brain is much more complicated than a processor. But for this example, if the brain controls and coordinates all the parts of the human body and all the different systems, then a CPU fulfills the same function. So there are 8 cores in this particular CPU, meaning that there are 8 of these central processing units. The more cores your processor has, typically the more powerful the chip. Power in terms of computing means it can perform operations fast and to some degree efficiently and effectively. So the more the core count, typically the more powerful the device. And power means faster processing in general. Then it talks about having a 10-core GPU. So again, here you're talking about the graphics processing. The more the cores of the graphics processor, the more graphics the system can render. So when we talk about graphics, we're talking about images that appear on the screen. So the more powerful your graphics processor, the more graphical fidelity you get. In other words, the clearer the image, the faster the image, and the more technically complicated the image can be drawn. So it's a factor of power, capacity, and speed. So the more the core count of the GPU, the more graphical prowess your system will have. Then you have a term here called 8 gig. It doesn't just say 8 gig of RAM. It says 8 gig of unified memory. The concept of unified memory is very interesting, and we'll touch on it later on. This is an architecture specifically for this particular chip. This chip is called the M3 chip from the Apple Silicon lineup. So we are going to be looking at generally the architecture of a computer and come back to understand why this term unified memory is so important. Then here you have 512 gigabytes of SSD. What does gigabyte mean? What does SSD mean? SSD stands for solid state drive. It's a type of technology that allows storage devices to have high capacity, high read and write throughput, as well as good energy efficiency, shock resistance, and to some degree affordable. They're still quite expensive compared to magnetic disks. But the point here is when you're looking at this ad, your goal as an IT person is to understand the full capabilities of this system. And you are concerned with answering the following questions. One, is the computer fast enough to run the programs that I'll be utilizing? Last week, a couple of students were asking me if we wanted to buy a computer for our study, what kind of computer should we buy? Well, the first question you need to answer is the computer enough to run necessary programs? Now, like I said last week, every computer in the marketplace right now is plenty powerful. I mean, it will serve you and it will serve you well. There are other factors that you need to be concerned with. So, for example, if you're concerned with battery life, you want to look at the efficiency of the system. If you're interested in using your computer for things other than just schoolwork, maybe you want to also use it as an entertainment center, you want to play games, then that will define what kind of system you're going to get. So is it powerful enough to run the programs you want? Next, is the computer cost effective? As you can see in this particular ad, these systems here are not particularly cheap. It starts off at 7,500 ringgit. There are cheaper lineups in the Apple ecosystem, which will also serve. But here in this example, these would be considered somewhat expensive. Although they're very powerful, they are still quite expensive. So again, do you have enough money to be able to justify this particular expenditure? In other words, are you getting bang for your buck? This is not a question of whether the device is expensive or not. Is it going to be useful to you? And will you be able to pay that amount for the utility you get? The last question you will be dealing with is, will it be obsolete in a few months? Now, typically, the Apple computers are very expensive because they have good longevity. A typical Apple computer will last up to 5 years plus. if you take care of it even longer. And the Apple company maintains support for many of its hardware 10 years or even more into their life cycle. Many other manufacturers, they build devices that are not very durable, and they won't get operating system support for the entire duration. They won't certainly get up to 10 years. So for example, if you're looking at the Windows 11 laptops now, if you have a device that is 4 years old, it won't be able to run Windows 11 because of some security chip that the Windows 11 architecture requires. So there are lots of things. So by the time we're done with this module, you should be able to understand these discussions and understand why it's important to appreciate computer architecture. So with regards to the importance of studying computer architecture as a user, what's a user? A user is a person such as you who buys a device for personal use. So a regular user is very different from a power user, which is also different from some sort of professional that is buying the device for some job function. So we're going to look at a few examples. As a regular user, you want to understand the system capabilities and limitations. Why? So that you will know if this device can perform the actions that you want. You want to understand architecture so that you're able to make informed decision. In other words, you don't buy something, go home, after you set it up, then you're like disappointed because there's one particular thing that you really need, but it cannot do. And you didn't find out till you've already paid the money. Also to improve communication with technology professionals. Sometimes you will maybe look at a review of a device and you're still debating whether to choose between 2 or 3 devices. A good practice would be to go into the marketplace and start talking to the market salesman and find out a little bit more about the device. So the understanding of computer architecture will allow you to be able to interact and engage with these people in such a way that they will be able to provide you more details and more information with regards to the capabilities of this device. As a programmer, so if you're going to be building applications, one of the key things you need to pay attention is all applications require resources. They consume resources. So if you're building for a particular platform, the way you're going to write your code is going to be different. So what I mean is, if you're writing an app for a mobile device, it's a very different paradigm from if you were writing for a desktop environment or for a web environment. So for example, if you're building a web page, so you're building a web app, your web app has to be dynamic in the sense that since mobile phones, tablets, and laptops with many different screen sizes are going to be able to view your web page should be able to resize and reorder items effectively. Otherwise, it won't be suitable for some platforms. So if you design it for a desktop and you're strictly designing for desktop, if somebody tries to view that web page from the phone, it's going to be very cumbersome to actually navigate the page. So understanding computer architecture for the programmer helps them create efficient application software for specific processing needs. So if it's an application you're going to be building for a specific use case with a specific set of device, you need to understand the architecture of the device. If it's for generic devices, then you have to build your applications in such a way that it will be able to fit into these different device architectures. You also want to understand computer architecture from a system architect or analyst's point of view. The system architect or analyst is the person responsible for purchasing technology hardware for a company. So if you look at the university, for example, we have 10 floors, and in these 10 floors, we have about 3 blocks that are just classrooms. In every classroom, there's a projector. We have a bunch of labs that have different desktop setups and so on. Somebody had to decide what model, what brand to actually purchase. That person is called the system architect. Their main job is to understand architecture enough to be able to specify computer systems to meet the requirements of an organization. That means when they're purchasing, they are purchasing in bulk. They are not buying 1 or 2 computers. They're mainly concerned with several things: the cost of the device, the quality of the device, as well as the time to service. So if I'm buying something for an organization and they're going to be using it for work, I want, if any of the devices encounters a problem, maybe something breaks or something isn't functioning and I need a service person or I need to repair a component, I want to repair it as quickly as possible. The longer the system stays down, the less utility I get from that system. So as an organization, uptime is very important. Think about it. If you as a student, you are technically a customer to a university, you've paid for a particular service, and when you go, let's say you go to a class and your lecturer is trying to set things up, and then we find out that maybe the projector is faulty or bad. For the duration where that projector is faulty and bad, it's going to compromise the efficiency or the effective delivery of the lessons. So if the lecturer wanted to actually share something on screen, they wouldn't be able to do so for the time that the projector is bad. So if this projector is made from a company and we send it back to the company for servicing, the faster they're able to service it, the better for us, because we will have less downtime. Because effectively, if a projector isn't working, a classroom is effectively useless. So this is the factor that we talk about here called time. So from a system architect's point of view, the cost of the device, because they're buying in bulk, the quality, the durability, how easy it is to, how durable it is in terms of resisting faults, because again, these equipment will be used by multiple people. So because you're going to be dealing with, some people are gentle, some people are rough, you want something very durable. That's quality, and time means time to service. Then from the point of view of a system administrator, which is essentially a network admin, their job is to understand the architecture enough for them to be able to install operating systems and applications, configure those systems, maintain and upgrade the systems whenever there's an update. So let me give you a good example. If in the university we have several labs, and in each of these labs there are several computers, so total the university will have a couple of thousand devices. So those thousands devices, eventually, every now and then, will need their operating systems updated or patched. Now, if the system administrator was to go one by one and try to update these devices, imagine the amount of time it would take to update 1,000 computers and how much bandwidth you're going to consume while downloading the file. So let's say there's an update or a patch that is 1 GB and you have 1,000 computers. So if each and every one of these 1,000 computers is going to download that 1 GB file, then you'll end up with 1,000 gigabytes times 1,000 computers. That's a lot of bandwidth. But with the system administrator, what they can do is, depending on the different operating systems that they have in the organization, they may only need to download one copy for every operating system type. And then from the central network, they can broadcast that update to every device and effectively update all the computers in the university in just a few hours, as compared to if you are going to go device by device, one by one, one by one. So understanding computer architecture helps you recognize how you can be able to leverage the system administrative functions of operating systems. Also maximize system availability and efficiency. That is to ensure that everybody using a device in that particular network will be able to use the device, and the device will run buttery smooth, and the network will not be impacted or affected in the least. And lastly, to optimize system performance. So they need to understand computer architecture for those tasks, and also security. For a web service designer, which is basically a programmer for websites, they need to understand architecture, like I mentioned, to optimize the experience while using these web services. So these web services are designed to run on different types of platforms, whether mobile or desktop, as the case may be. So you need to know the data formats, how to lay up the page, and how it will appear on different devices. Lastly, uh, to put it in a concise conclusion, the study of computer architecture is very important in understanding capabilities of a system and knowing how to work with the system in the most effective manner possible. So here we have the general architecture of a typical computer system. Now, the term architecture, if you hear that word, the image you should get is that of typically a diagram that is describing some sort of system. So in a computer, last week, when we defined what a computer was, we said it's an electronic device that can accept input, process that input via a set of instructions, and generate some sort of output that can be stored or communicated. So in a graphical representation, this is what a computer's architecture would look like. So the input box here represents all the input devices. So this can be your keyboard, your mouse, your microphone, your camera, and so on. Then you have the processing devices, which can include your central processing unit, your graphical processing unit, your network interface card, and so on. And then your output devices, which include your screen, your speakers, and so on. And then, of course, your storage devices, which is the medium that stores data that has already been processed or data that is going to be used in the future. So this, in a nutshell, gives you the overview of the architecture of a typical computer system. So we call this the process model. Input, process, output. All computer systems will operate in this manner. Input is the information we take from the real world. Processing is the instructions that we follow to transform that input into some sort of output, and then the output is the result generated. In order to drive this message home, let me switch my screen to my whiteboard, and then we can take a look. Right. So can everybody see my whiteboard? Can I just get reactions? All right. So let's go ahead and do some definitions. So here now, we've defined a computer as essentially, so I'll just make a quick document here. So we've defined a computer as an electronic device that can take in input, process that input via a set of instructions, and generate some sort of output. So what do these terms actually mean? We mentioned last week, electronic device means powered and controlled by electricity. So it's very important for you to understand this: powered, not just powered, powered and controlled by electricity. So just excuse me, the tablet is a bit small. The input represents data in the real world. I'll give an example in a minute to make that make sense. So data in the real world. Processing via instructions. Instructions refers to software. So a software program. So this software, remember from last week's lesson, we said it can be system software, which is the operating system, or it can be application software, which is the applications you install on your computer. The output is the result of computation. So now it should start making some sense. In other words, let me give you an example. Let's say in the real world, this is me, for example. And let us say I have 6 apples, right? So this is me. I have 6 apples. And I have 3 friends visiting me. So there's friend A, there's friend B, and there's friend C. So let's say I wanted to entertain these friends and welcome them. So I wanted to share these 6 apples with these 3 friends. This is the problem I have. So I want you to imagine for a second, if you didn't have any mathematical knowledge, how would you go about solving this problem? You need to conceptualize that, of course, you have 6 apples and you're going to be sharing it with 3 friends. So how are you going to do it? So rudimentarily, you could think of doing it this way. I'll take 1 apple, give it to the first guy, then take another apple, give it to the second guy, then take another apple, give it to the third guy, and then repeat. Give another, give another, give another, give, till all apples are done. So in other words, you are performing a mathematical equivalent of doing 6 divided by 3. Does this make sense, people? Can I get a quick thumbs up? So what you're seeing now is the real world problem is that I am a guy who has 3 friends and 6 apples, and I want to share the apple. That's the real world problem. So everything here in this dotted black circle is the real world problem. This real world problem is represented mathematically here. So this is a representation of the problem. Does that make sense? The real world problem is one thing. 6 divided by 3 is a representation of the problem. So what's the meaning of this word representation? The simplest definition for representation is instead of, in place of. So representation can mean in place of. In other words, anything that can be in place of another thing. So what are we talking about here? This 6 is a data value. And this data value represents the number of apples. So it's a data value that represents the number of apples I have. This 3, it's also a data value that represents the number of people I have. And this divide function is a data element that also represents the operation to be performed. So we can say operation or function, basically representing the problem. Does this make sense to everybody? So this 6 divided by 3 is a mathematical equation. You can see that the 6 does not necessarily say 6 apples, because mathematically, when we're performing a divide function, we don't care if we're dividing oranges, apples, or guavas. It doesn't matter. We just need to know that there are 6 elements and there are 3 entries, and the function is an addition, subtraction, multiplication, or division. It represents a solution to a real-world problem. Now, I want you to think about this. If we wanted a computer to compute and give us a result for this particular real-world problem, how would we do it? This is what that model, which you just saw, is doing. The model, the IPO model that we just looked at right now, reveals something about the architecture of a computer. It says all computers, no matter how complicated or simple, will operate in this way. There's the input, then there's the process, and then there's the output. So input, process, output. So in the divide problem that we have, what is the input? The input is the information that we have 6 apples. It's also the information that we have 3 people. And it's also the information that we want to perform a divide function. So we want to perform a divide operation. So we have to find a way to represent all of these data points and insert them into a computer. So to do that, we need an input device. In this case, the input device for this particular problem would obviously be a keyboard. Why would it be a keyboard? Because we're taking values 6, 3, and a function divide, all which are represented on our keyboard. So the input is a way we can pass a signal to a computer, but the signal has to be configured with some sort of meaning. So when we're inputting something in a computer, there are generally 3 things we can, actually 4 things that we can input in a signal. 1, we will come back to this at a later date. A signal can represent power. So in other words, I can plug in my adapter into my computer. It will generate an electrical signal, which will charge the battery. So a signal can represent power. I can plug a USB hard drive and I can read and write to the hard drive. So on the cable connecting to the hard drive, I can send an address signal. That address signal will tell my computer which part of the hard disk to read to or to write to. Then I can also have data in the signal. The data can represent one of two things. It can represent just pure information. So for example, I could copy a music or a video file into my computer via an input device. Or like in this example, we can pass on an instruction. So what is the instruction? Mathematically, the instruction is 6 divided by 3. Does that make sense to everybody? Can I get thumbs up? All right. So the input represents information about the real world that is fed into a computer. So the device, that input device, what it tries to do is it changes the nature of the signal to make meaning to the computer. Like you as a human being, if you can speak English and I speak to you using sound, the sound has to hit your ear. So your input device is your ear. When that sound hits your ear, it's converted into an electrochemical signal that is then sent to the brain. So the input device converts every signal relating to information in the real world into a digital form of electricity that the CPU can understand. So once that input comes in, the next step is we can begin processing. So processing, to process means to transform. And we transform things via a set of instructions, which is software. So we transform things via a set of instructions. So if we have a piece of software, the software will be a file that consists of lines of codes, and these lines are instructions. It will tell the computer exactly how to go about transforming that input into some sort of meaningful output. In other words, as a human being, if I ask you, what is 6 divided by 3? 6 divided by 3 is obviously 2. So you can interpret that result as each of the 3 people gets 2 apples. 6 divided by 3 equals 2 means 2 apples for each person. Now you're able to perform that calculation because you know the instructions to follow to perform the mathematical operation of division. You learned it sometime in your primary school. So the program is basically knowledge, know-how, the technical specifics of how to transform 6 divided by 3 into 2. Does that make sense to everybody? So the program will detail the individual steps and processes we will follow to transform the term 6 divided by 2 so that it equals 6 divided by 3 so that it equals 2. Now, once the computer has done that, it has used the input and the instructions. So let me label these things properly. We have now used the input, which is step 1, and we have also used the instructions, which is step 2, to transform the input into some sort of output, which is step 3. So step 3 refers to the results. So the results now, in the case of 6 divided by 2, 6 divided by 3 is, of course, 2. So this 2 is now the result that we're dealing with. Now this 2, remember, it's generated inside our processor as an electrical signal. But human beings can't speak electrical signal. So if the computer tried to broadcast that electrical signal to you, it would be useless to you because you don't have any sense organ to receive that electrical signal. As a human being, you have 5 senses. Your eyes deal with light. Your ears deal with sound. Your tongue deals with taste. Your nose deals with chemical signals that can stimulate. And then your skin has a number of sensors. There's texture, and there's also temperature and so on. So now what the computer's output device needs to do is it needs to convert this electrical signal into a form that you can understand, which means this results needs to be pumped out. And when it is pumped out, it can be pumped out to a screen, in which case you will see the character 2 as the result, or it can be pumped out to a speaker, in which case the computer can say 2 and produce sound to represent the output 2. Am I making sense? So the job of the output device is to transform the signal that is the result into a format that the human being can understand and engage with. So by doing this, the computer takes the place of a human being and performs the action or the activity that a human being can perform through the power, of course, of software instructions. So as long as you can define the instructions to transform an input into output, your computer can perform the job without any issue. So this is the first bit regarding the input process model that I was just mentioning. So I will switch back to our slides. So just give me a minute. There we go. So let's jump back to our slides. So hopefully you can now see my screen. So when we discuss the IPO model, which we went into detail just now, we understand now what input process output really means. And why are we studying it? So the input can represent any device that can generate a signal that is fed into a computer. And that device usually, when it generates something, it tries to format it in a way that the computer can actually understand. And it represents some type of real world problem, as it were. With regards to the processes, they execute instructions according to the code that has been given. Then, when you look at the output devices basically allow the computer to convert back the instructions, or rather the results, and provide it to a human being in a manner that the human being can accept. And then for the storage can be different types of mediums. So you can have a hard drive, a magnetic hard drive, a solid state drive. You can have diskettes, magnetic tapes, and so on. Now, these storage devices, their job is just to store the binary values that make up the data, the zeros and ones, as it were. So is that clear to everybody? We can move on to the next item. Can I get quick thumbs up? All right. So let's move on. Now, taking a look here, we have a web browser application. Now, in this web browser example, we are again looking at the architecture of a computer. But the difference here is, whereas the IPO model, we were looking at a single computer, a single standalone computer system. This web browser application and how it operates in an IT system. Computer system, one computer. IT system, group of computers transmitting and exchanging messages with each other. So there's a fundamental difference between a computer system and an IT system. A computer system is one computer. An IT system, multiple computers on a network, along with some hardware and some processes and a bunch of other things. So a web browser application is an IT system. So when we look at this architecture of this IT system, what can we tell with regards to this architecture? What are the things that we can understand? Well, let's take a look. So I'm going to take a snapshot of this. So from the snapshot of this particular screen, we can begin to diagnose every single piece of this item, right? So let me go ahead and take a snapshot. I'll need to switch my screen once more so that I can draw out what we're taking a look at here. All right. So hope everybody can see my screen. So here, I'm going to zoom into this part of our application. So the architecture here shows us first and foremost, there's this guy, the user. What's a user? A user is a person who makes use of a computer or any sort of device. So that's the user. This arrow here pointing to the keyboard, hold on please. This arrow here pointing to the keyboard is specifying that we're typing a bunch of characters. And these characters represent information about the problem that we want to solve. In other words, we're giving a URL. This URL stands for Universal Resource Locator. It's the address of an item on the internet. So when we type it into the web browser interface. So here we have a user interface for the web browser. The web browser then takes this URL and then formulates it as a page request and transmits it over a communication channel. This is our internet. So once it arrives the internet, there's some technologies that help the message get to where it's going. So here it's coming to a web server. So the web server here does the processing of that request and then generates a HTML. So what's a HTML? A HTML is a file with markup code that draws out the details of a web page. So it contains zeros and ones that tells the computer how to draw basically a web page. So when that HTML file comes back to the web browser, it's now rendered and we can see the result. So what goes on in the communication channel is a subject that you will cover in networking. Meanwhile, from here, we can see the entire architecture of communication for a web browser application. So what are the things that we can actually learn from this? We can learn that one, there's something called a URL, and a URL is an address that points to a resource online. The communication channel is basically the internet, which consists of several dozen routers, switches, hubs, and all these network equipment, and they each have a specific type of functionality. So I'm going to jump back to my primary computer, and I'm going to show you yet again another example. So let's say I go to the Apple website, for example. So I go to apple.com. Now, let me go to the Malaysian site. There we go. So here we're seeing basically the web page. So what I did was in the address bar, I typed in a URL, apple.com. When I hit enter, my web browser application transmitted it using my network interface card, did a little bit of processing, and the results were generated. So what I'm now seeing is something that is coming from the Apple service, but this is not the form I receive it in. So if I go to view page source, the web browser will show me the zeros and ones or the characters that were actually transmitted by the Apple server. So this is the HTML file, the hypertext markup that was sent back. And you can see it's a couple of 100 lines of code. So my web browser is taking these 100 lines of code and rendering it into the characters, the graphics, the images, the video, whatever it is that you're actually seeing on screen. So this is the actual code that generates it. And this code is transmitted to my computer as an electrical signal. It is the web browser that takes the zeros and ones that make up that electrical signal that transforms it into this character. And then the web browser uses the characters to generate the images and the text that you can see in this nice little website. Is this clear to everyone? So you can quickly begin to see how the study of computer architecture actually opens up our eyes to the nitty-gritty functionality. And we've not even touched the surface. This is just the surface. We've not gone in deep. So like I mentioned, the communication channel will be discussed in your networking subjects. Now, doubling down on the concept of information technology, an IT system is similar to what you see on screen here. Here we have a list of the human body system. What's a system? A system is a group of interrelated components working together for a specific function. So some examples of the human body systems here is the digestive. So this consists of all the components of the human being that are related to digestion of food. So this includes your mouth, your throat, your stomach, small intestine, large intestine, and so on. For your cardiovascular system, its main function is to supply the body with blood and oxygen. So the oxygen is in the blood. So to move blood throughout the body. So it consists of the heart, the veins, the arteries, and a few other components, and so on and so forth. So every one of these systems is unique in terms of its primary responsibility, but all together they form a human being, a full, complete human being. In the same way, an IT system is similar to what you're seeing. So here is an IT system layout. So what is it that you're seeing here? Similar to the human body, you can see that there are a group of systems. So for example, there's a group of computer systems here labeled sales. You can see them here. These are labeled sales. Then you have another group of computer systems labeled finance. Then you have another group labeled marketing. Then you have another group labeled order fulfillment. Similar to the human body, digestive system, respiratory, and so on. So what is the fundamental difference between all of these computers? They're all computers after all, so what's their difference? We can ask the same question looking at the human body system. What's the difference between the digestive and the cardiovascular system? What's the difference? I want you to think about that question. What's the difference between the digestive and the cardiovascular? The digestive system is made up of cells as well. Everything here is made up of cells. So what's the difference between the cells in the digestive systems or the organs that make up the digestive system versus what is in the cardiovascular? It is their primary purpose, how they operate. So in the same way, the difference between these computers here is just what function they serve, what software they are running, essentially. So the sales, although they have computers, the software that they're using is different from the one that is used in finance, which is different from the one used in marketing, which is different from the one used in order fulfillment. But they're still computers. They have the same components, input, process, output. The only difference is their software. So this brings home the real important distinction. An IT system consists of multiple systems, including their hardware and their software, and the people that use them and the roles and responsibilities they face. So an IT system operates like one giant organism. Data is being transmitted from different departments or different sections to fulfill an organizational's need. And at the top, you have the servers, which are also just computers with specific functions. So let's take a look at a couple of things with regards to the servers. Here you can see, first we have a firewall. If you don't know what a firewall is, it's basically a special device. It can be a computer running a software or a dedicated device that has software that tells the computer's network how to filter information. Think of it like having a security guard at the entrance of your home. If the security guard is standing there and has been given instructions, do not allow any unknown person or any person who is not invited to the party to come in. So the guy becomes like a bouncer. When you come, you introduce yourself, you show an ID card, the guy validates your ID card. If you're good, then he allows you to enter. If you're not, he prevents you from entering. So this is essentially what the firewall is. So you will notice, look at all the cables connecting the different groups. You can see the order fulfillment has a network cable connecting it to the primary switch, and that switch is then connected to the firewall. In other words, all of these computers here, none of them are connected directly to the outside world. All of them are connected to the firewall, and the firewall is then connected to the internet, meaning that any message leaving or coming in has to go through this firewall. And this firewall is like a security filter. It prevents things from going out, and it also prevents certain things from coming in. So it's not that it's just filtering what's coming in. It's also filtering what's going out. So again, you begin to see the importance of studying architecture. Just by looking at these lines, if you understand computer architecture, it tells a story. What is an internet service web server? This is the computer that generates websites for this organization that can also be shared on the internet. What's an application server? It's a special computer where all the applications are stored for this organization. So if a person from order fulfillment wants to run a particular app, they don't necessarily need to install it on their computer. They can run it off the application server. So the application server has the software already pre-configured. All this guy needs to do is log into this application server and then run the application. So you see now, if I'm a network administrator and I wanted to give everybody the ability to use a certain software, rather than installing it on every single computer, I can just install it on my application server. Then you have a database server where all our databases are stored. So all the data of our organization. Again, it's one central location. If anything needs to be monitored, maintained, corrected, edited, updated, it will be done on this server. And it can then be accessed by everybody. And then you have the internet web server. So there's the internet and there's the intranet. The difference between inter and intra is internet regards the general network, the global network. So the organization and other networks outside of it. The intranet, it's basically the organization's own network. So I can have a service that is only accessible within my organization. People from outside cannot view it. So for example, this application that we have, the one that we use for taking attendance, this app space is both an intranet and an extranet application. So we can run it inside the organization. Let me just open up app space, not Apple, app space. So we can run it. There's an internal version and then there's a network version of this particular application, this app space application. So I hope that makes sense to everybody. Can I get a quick reaction? All right, so moving on, we're almost done. So now coming back to a typical computer system, it's important to note that all computers, no matter how simple or complex, will consist of the following items. It will have at least one CPU. Typically, computers today have more than one. So when we talk about the CPU cores, we're basically saying that our computer has multiple CPUs, but a CPU nonetheless. So you have to have at least one CPU. Then you need to have memory to hold the programs and the data that you're operating on. And then you need to also have input and output devices. This is the means by which you will communicate with your computer. The input devices allows you to pass messages and data into the computer, whereas the output devices allows the computer to now communicate with you by presenting data in a form that makes sense to you. And then lastly, storage. So if you're asked what are the four primary components for every computer, you will say at least one CPU, memory, then input and output devices is one thing. Is not input device one thing, then output device another thing. Input and output device are a unit, and then long-term storage. So CPU, memory, input, output devices, and long-term storage. Remember that. So when looking at the hardware, looking at the components of a computer system, like we mentioned in our introductory session, you can describe a computer and classify all of its components into the following. You have the hardware components, which consist of all the physical components that you can see. So that's the input devices, the output devices, the processing devices, and the storage devices. Then you have the software component, which itself consists of two other subcomponents, which includes system software or the operating system and application software. Then you have the data that your computer can generate or can store. And then you have the communications equipment, which includes the network interface card. So for the communications, you actually have two components. There are hardware for communication and also software for communication. So this is how we can classify the components of a computer system. So for the hardware components, like I mentioned, it includes the input, output, storage devices, and the CPU. The CPU itself is made up of other components. So we will have a special lesson where we will concentrate and learn about the architecture of the CPU specifically and how it operates. But for now, these are its components. Then, of course, you have the memory, which is a storage area for short-term operations. So all of these components make up the hardware of a typical computer system. In diagram form, here's how they're all connected. So this is, again, another architectural representation of a computer system. Don't forget, the IPO model we saw just a couple of slides ago, this one here, it's also the architecture of a computer system. So in other words, we can build architectures, multiple different types of architectures for the same system to show different aspects of the system. So the IPO model is showing you the fundamental components, whereas this next one that we're looking at is showing us the hardware architecture, how the hardware components are actually connected. So here you have a bunch of input devices and a bunch of output devices, and it shows you how they're connected to the CPU and the memory. The CPU and the memory are at the center of all of the processing functions. So looking at the CPU, it consists of something called an arithmetic logic unit, a control unit, and a bunch of registers, as well as an interface unit. So the arithmetical logic unit is the part of the CPU that performs arithmetic and Boolean operations. The control unit controls and coordinates all the activities of the CPU. So listen to this. Your central processing unit is responsible for controlling and coordinating all the activities of your computer. Then your central processing unit itself is made up of several components. One of those components is called the control unit. So the control unit controls and coordinates all the components of the CPU. So the control unit is to the CPU what the CPU is to the computer. I hope that makes sense. It controls all the activities of the processor. And the interface unit allows for translation between signals coming in and leaving the CPU. So if you look at this diagram, once again, you will see that the interface is this layer that all other devices connect to. So think of it, you can have a hardware interface. So if you have a USB port on your computer, when you connect when you connect a device via USB port, the interface is the USB port. So what we're showing or demonstrating here is that there's a port that allows all of these devices to connect via the motherboard to the CPU and to the memory. So that's what this architectural diagram is actually communicating with us. So far, so good. Lastly, a bus is the wire that exists between components that carry signals. So if I have any type of diagram, that diagram, any line on that diagram that indicates data is being transmitted from one place to another will be considered a bus. So what is a bus? It's just a wire that carries a signal, full stop. Nothing more, nothing less. Now, we want to understand what the memory actually is like and how the computer actually works. In order to do this, I'm going to use an analogy. And an analogy is a way to describe or give an example to help you understand what's actually going on. So I'm going to open up and I'm going to search for a person on an office desk. I'm just looking for an image, and I'll use the image to describe the paradigm that I'm trying to explain here. So let me zoom in. So here in this image, we have this gentleman. This is a person sitting in his office working on his desk. So the Windows computers, the Windows operating system actually uses this analogy. Where do you go to work? You go to the office. So Windows has a set of software application called Microsoft Office. So what do you do when you're in the office? You create documents. So there's Microsoft Word for publishing documents. You might invite people for a meeting and have a presentation. So they have a software for that called PowerPoint. You might want to draw images and pictures to help communicate. So there's OneNote that you can also share. I think you're getting the idea. So the Windows operating system was designed for office users. So everything about Windows computers is about getting work done. So when you're going to sit down and get your work done, you sit at your desk and your work is on your desktop. And that's the name of the interface of your computer. So this, for example, if I zoomed out, this is my computer's desktop. So on my desktop, I can have a bunch of tools and a bunch of software that you can see here. So these are all my installed applications and software that I use for my day-to-day task and my day-to-day operations. And you can see the Microsoft Office suite down here as well. So what I'm trying to get at is the analogy here is the same as the analogy that Microsoft Windows uses, but it's also the same for all computers. So let me go ahead and explain. When we looked at the concept of memory, what is memory and how does it fit into the description of how a computer works? Well, this is how it works. I want you to imagine this guy has a bag, an office bag that he comes from home with. So inside the bag, he might have his laptop, a bunch of books, a calculator, and some documents. So when he gets to the office, he takes off his bag, opens it up, and takes items from the bag that he's going to use, and he places it on his desktop. So this desktop is like your memory. The bigger the memory, the more things you can open and place on top of it. And you will not be able to read or use any tool until you take it out of your bag and you put it on top of your desktop. Your bag is like your hard drive. That's your storage device. So you can have things in your storage device, but you cannot open them whilst they're in storage. So in a computer, your storage is your hard drive. Everything that you have stored in your hard drive, if you want to open it, you have to copy it from the hard drive onto memory. This is how computers work. You have to take it out of the hard drive and bring it into memory. So when you bring it into memory, then only can you read, write, and modify, edit, or perform operations on it. Does this make sense to everybody? Can I get a quick thumbs up? So this is, I think for this chapter, the most important concept to actually understand. So to drive home this concept, I'm going to give you one example. So I'm going to switch over to my whiteboard and we're going to draw a diagram. So let's go to the OneNote. So let's go ahead and draw a very important diagram. So here I'm going to draw a diagram representing a full-fledged computer. So this box is going to represent my hard drive. So this is my hard disk drive. Then I'm going to draw another block that is going to represent my RAM. So this guy is going to represent my random access memory or just my memory. I'm going to draw another block that is going to represent all my input and output devices. So these are I/O devices. And then I'm going to draw another block that is going to represent my something called a cache controller. So CC for cache controller. I'll explain what this means in a minute. Then lastly, the actual CPU core, which itself will consist of 3 other boxes. So, oops. Let me just undo that. There we go. So there will be a box here. I'm not sure what's going on. All right, at least we can move you and resize. All right. So this will represent the CU. Then I will have another block. This will represent the ALU. And lastly, one to represent the registers. So let me just note them. So this is the control unit, this is the arithmetic and logic unit, and these are the registers. So this is the typical architecture you would have on a computer. Now, this entire blob here is actually the CPU. So this guy, this entire thing here is the central processing unit. So connected to it, this wire you can see it's a bidirectional arrow. These black wires are the buses that we mentioned, cables that carry signals between components. So it's a bidirectional arrow. So far, so good. Does this diagram make sense to everybody thus far? So I'm going to give you an example here. If you were going to say, try to understand how a computer actually operates and how it functions, we can now use this diagram to better understand it. So let's say on my computer, I have a music file. That music file will obviously be stored somewhere in my hard drive. And in the hard drive, it will be a file that consists of a sequence of zeros and ones. That's how the computer stores things, zeros and ones. So let's call this Michael Jackson mj.mp3. So this term MP3 means that the file software, the software that can open and operate this file has to be an MP3 player. Then here, I have another file, which is the software that I'm going to use to play this MP3 file. So let's say I'm using VLC.exe. So this VLC is essentially also a file that consists of a bunch of zeros and ones. So you might say to yourself, wait a minute. If both files contain zeros and ones, what's the difference between the two? The zeros and ones in this file refer to data that I can use to produce music, whereas the zeros and ones on this file represent instructions. So you might be thinking to yourself, I don't get it. Can you be more specific? Well, think of it this way. Right now, I'm speaking English to you, and I can use this English to tell you a story. Once upon a time, such and such happened. That's the MP3 file. It contains data. So thing happened, and I can tell you a story. I can still use the same English language to say, sit down, stand up, go buy me coffee. And that would be me using the English language to pass on instructions, which is what the VLC is. So in your computer, these zeros and ones represent electrical signals. And these electrical signals can be used to represent data or instructions. So 6 divided by 3, like we did a few minutes ago, is an instruction. Take the data element 6 and take the data element 3 and divide them by each other. That's an instruction. So an instruction can also make use of data. So the VLC instructions will basically say, computer, read this MP3 file and transform all the zeros and ones into sound, and then pipe that sound out to an output device like the speaker. Or if I'm using my Bluetooth wireless headset, it might say, send it to the network interface card so that the network interface card's Bluetooth antenna can then transmit it as a radio wave. Am I making sense? All right. So now let's say I want to play this file. In real life, what happens? This is what happens. Both the MP3 file and the VLC file, so I'll just make a dotted line around them. Both of these files are copied onto RAM. They are not transferred, they are copied. So you basically make a copy of the file onto RAM. Now, when you make a copy onto RAM, it will occupy some space in RAM. So let's say it occupies a few megabytes, right? Let me quickly show you something. I'm going to attempt to right-click on my taskbar, and I'm going to, let me try that again. Right-click on my taskbar, and I'll enter my task manager. So here on my task manager, you can see the list of applications that are running on my computer, and you can see how much memory they're consuming. So if you look at this table here, you can see that this MS Teams update is consuming about 1 gigabyte of memory. That is my RAM. In other words, all these applications, when you open them, they occupy space on your memory. So my operating system is monitoring who is using how much of my CPU processing power, who is using how much of my memory. So here it says 89% of my memory is in use, and 1,800 megabytes of that is used by the Microsoft Teams update. My OneNote is using 149.3 megabytes, and so on and so forth. So that's what's being communicated here. Whenever we open files, whether they're data files or instruction files, they will occupy some space. So the more applications I have open, the more full my RAM would be. When my RAM becomes completely full, it means I can't open any new applications except if I terminate or offload some others. So you will typically notice if you have little RAM, like 8 gig, if you open a web page with many tabs and you open multiple applications, maybe you're browsing the internet and you're listening to music and you're doing a bunch of other things, maybe you're even using an antivirus software and a VPN, you're consuming space. So at some point, your computer might start to slow down. So your computer slowing down might be an indication that you have your RAM is too small. So for people who are using 8 gig, if you want better performance, try not to run multiple applications at the same time. It's not a processing issue, it's a RAM issue. So now, once you've made a copy, the next thing that needs to happen is the CPU needs to now start reading the instructions and performing the operation. So the VLC instructions are like a cooking recipe. It's list item 1, 2, 3, 4, 5. So it's a list of instructions. And those instructions will have to do with copying some part of the data file, that is the Michael Jackson file, and transforming it into audio. So let's say we actually wanted to play music. What happens? Step 1, we make a copy onto RAM of the program. Step 2, the instructions from this program, both the data file and the program, will be fetched by the CU. The CU will issue an instruction to fetch. Just like a human being, when you're reading a book, you don't open all the pages of the book and download it into your head at once. No, you read the book page by page, line by line, sentence by sentence, word by word. So this fetch is taking line by line, a line of instructions. So instruction 1, instruction 2, instruction 3, and so. So the CU will fetch. Then once it fetches, it will then decode the instructions. Once the instructions have been decoded, that means I read and I understand what I'm supposed to do. Then I execute. To execute, it passes it on to the arithmetic logic unit. So the arithmetic logic unit then performs the actual execution. It does the transformation. Once the transformation has been done, then we store the results in the registers. So we store the result in the register. Hold on. So we store the result in the registers. And the registers are basically like the RAM for the CPU. So it consists of blocks where we can store things. It's like a shelf inside the CPU. So once we finish working on it, we can then generate the results. So the results now that have been produced will go back into the RAM. So there's a special space again in RAM that will hold the results. Those results will then be transmitted to the output device, depending on what output device it is, and then it can be given to the user. So the user can now interact with the input and output device and see the results of this computation. Does that make sense to everybody? All right. So we can switch our attention back to the main text. So as we were saying, that's the desktop analogy. So this is the concept of memory. So memory can be measured in bytes. Bytes are made up of 8 bits. So the smallest unit of data is a bit. A bit can represent a 0 or a 1 because computers store information digitally. Next week, we will be looking at data representation, so we'll understand more about these bits and how a computer can represent information in the form of these bits. But what I want you to understand is the English language is made up of 26 alphabets, which represent 26 distinct sounds. A is pronounced A, B is ba, C is ka, and so on. In the same way, The language the computer speaks is electricity, but the electricity, instead of 26 different formats like English, it's only made up of 2 signals, a 0 signal or a 1 signal. So in English, if I wanted to write a word, I would spell it out using characters. So for example, if I wanted to spell cat, I would spell it C-A-T. If I wanted dog, D-O-G. And both these words are made up of 3 characters. This is the same thing in a computer. Every character is basically a 0 or a 1, and I can bundle these characters in bits. So 8 bits make up 1 byte. 4 bytes make up 1 word. 2 words make up a long word, and so on. So we'll look at that in next week's lesson. Let's not get too deep into it, but we just want to understand that the memory stores information as a sequence of bits in a memory location. So now going back to the components that make up a computer, remember we said there was the hardware. So in case you've forgotten, let me just step back. We said here that we can classify the components of a computer into 4 parts. There's the hardware, there's the software, there's the data, and then there's the communication. We have just finished looking at the hardware. We now want to enter into the software. So for the software, what are the components that make up software? I mentioned originally there are 2 main software components, which is the system software and application software. And you can see them labeled here, application software and the operating system. So the image we have here on the right-hand side is a diagram of the architecture of an operating system. The reason why we call an operating system a system is because it's also made up of a group of interrelated components. So an operating system like the Windows or the Mac or the Linux is not one piece of software. It's actually hundreds, in some cases even thousands of small pieces of software. Each software is responsible for a particular function and can be classified in a group. So here what you're seeing is the classification. So the operating system has something called an API. It has a file manager. It has an input-output manager. It has a kernel, and it has a network module and a bunch of other things. And we will be looking at this in separate lessons. So we will have a lecture specifically on operating systems, and we will get to understand all of these components. But fundamentally speaking, the operating system, all of the components that make it up, we can classify them into 3. We have the memory resident, memory non-resident, and the kernel, or the heart of the operating system, the main part. Memory resident is called the kernel. So let me repeat that again. There are 3 main parts or categories of software in an operating system. One is the memory resident, which is also called the kernel. That's the kernel you see here. Then there's the memory non-resident. Then there's the bootstrap program or the initial program load. We will again talk about this when we get to the operating system section. But these 3 parts have distinct characteristics. The kernel is the heart of the operating system. It's always loaded onto memory, and it is containing instructions that control and govern all the basic functions of the computer. The bootstrap program is the part of the operating system that helps load the operating system when you're powering on your computer. So when you turn on the computer, that booting process, there's a program that controls that booting process. It's called the bootstrap program. Another name for it is the initial program load. The kernel is the most important part of the operating system that is loaded immediately after you start up the computer. Then the memory non-resident are your utility programs that enhance functionality. Lastly, you have the communication components, which we said has its hardware and it also has its software. So the hardware for the communication components is the network interface card. It controls every communication that is coming in or going out of the computer. So whether it's wired or wireless. And then the communication components also have software that run and control them. So this network interface card has a piece of software that controls and coordinates its activities. So before we end today's lesson, I want us to understand the relationship between hardware and software. We say that hardware does the actual work, but software consists of the instructions on how to do the work. So the relationship between hardware and software is that the hardware needs to follow the instructions given by the software in order to operate. So think of it this way. As a human being, I need to learn how to do something before I can actually do it. So let's say I'm learning math and I want to learn division and I've been given a problem, 6 divided by 3. My brain needs to have a program that understands division. So when I want to perform division, my brain remembers the steps and the procedure to perform the division. So even though I'm using my eyes to see what I'm doing and my hands to write down the value 6 divided by 3 and do whatever rough work or calculation I need to do, my operation is guided by my knowledge of division. So that knowledge of division is the software program. And in order for me to be able to perform that software instruction, I need to have my eyes and my hands to perform the rough work. But at the same time, I need a brain that will read the instructions, understand it, and then allow my hands and eyes to operate on it. So what I'm saying to you is this. The most important hardware in a computer is the central processing unit. And that central processing unit is responsible for controlling all the other components. And in order for the central processing unit to control all the other components, each component has to have a software that tells the CPU how to control it. In the same way a human being in a kitchen wants to bake a cake, needs to follow a recipe, that human being is the processor. The brain of that human being is the processor. So the brain has to read the instructions, then tell the hands and feet what to do in order to control the other hardware in the kitchen to bake the cake. So the CPU has its own components. It reads operating system and application instructions, and then it sends a signal to the other hardware of the computer to perform an action. So that's like me going to my stove and putting the cake batter and then twisting it up. So I twist it with my hand. So my hand is part of the hardware of my CPU. My hand is connected to my brain. But my other hardware components that are part of my kitchen is my oven. Am I making sense, people? So I, as a human being, in my brain is my CPU, but my CPU is directly connected to some immediate hardware, my hands, my feet, my eyes, my ears, and so on. So I can read a cooking recipe, which is an application instruction, and then using my hands and feet, I can further extend and control other hardware in my environment, which is my computer system, input devices, output devices, and so on, to perform actions. Thereby, the CPU is controlling and coordinating all the actions of all the other hardware in a computer. But how does it know what to do? Software tells it what to do. And the two types of software that run on it are the system software and the operating system. For the network communication components, they have their own special set of hardware and their own special set of software, which are also part of the operating system, by the way. But that's just the idea. So the different types of computers, we can classify them based on their operation mode. So here you can see we have a laptop, which is part of the desktop environment. So the laptop, the desktop, the tablets, they're all part of the desktop computing space. Then you have the mainframes. Now what you're seeing here is actually a cabinet. This isn't the computer. The computers are inside this cabinet. So if I go to my web browser here and I search for a picture for a mainframe, what I will see in these images, let me expand these images. You can see here, we're seeing a man standing in front of a mainframe cabinet. So this cabinet, you can see that there are racks of different computers. So there are many computers inside the cabinet. So the frame, the mainframe, is a cabinet designed to connect many computers together to create more power and more efficiency. So companies that service or provide online applications like your Google search, your YouTube Music, Spotify, WhatsApp, they will be running on mainframes because each mainframe is like a server. and every server can handle a number of connected clients. So if, like Google, you have millions of users, then you need data centers with millions of computers. And these computers will all be rigged up together to operate like one super hive mind in a mainframe architecture. So the mainframe is just a cabinet that allows you to insert and install multiple computers, typically servers, to ensure power. Moving on, then you have your game consoles. So here you have the 3DS and the PlayStation. Um, of course, now you have the PlayStation 4, 5, and so on. So all of these game consoles are also types of computer systems. In fact, most of them run the Linux operating system. The PlayStation runs something called Orbis OS. Orbis is a form of Linux. The Nintendo also runs a form of Linux. Both the DS and the Switch, they run a version of Linux. In fact, you can actually install Linux and turn them into computers and they will work no problem. Now we talk about the concept of virtualization. A computer performs actions and operations. Everything a computer produces can be termed as virtual. So the term virtual means anything created or simulated by a computer or a computer network. So if it's something that is generated by a computer, it's virtual. What do we mean? If I'm playing a computer game, the game is a piece of software that generates an environment. So that graphical environment is a virtual space, it's a virtual world. It's virtual, part of virtualization. If sound is being generated by my computer, you know, I can have a musical instrument like a guitar or a piano, and when I play, I hear real sound. But for a computer, I can create digital versions of these instruments and have the computer speaker render those sounds. That's called, it's going to be a virtual instrument, a virtual that plays a virtual sound. So the term virtual has many applications. It just means something generated by a computer. So now we look at the term protocols. A protocol is defined as a set of rules that governs communication. So anytime two or more computers are connected together, they're essentially in some type of network. And in order for them to communicate, they need to have a protocol. No protocol, no communication. What's a protocol? Rules that governs how we communicate. So for human beings, when we want to communicate, there are some basic rules of engagement. When you see somebody in the morning, before you start talking to them, typically there's some type of salutation. Hey man, how are you doing? How was your day? Then you can start conversing. Do you know, you can ask them a question or you can tell them a story. So when you're talking to another human being, typically you will maintain eye contact, you will be facing the person, and only one person is talking at a time. So as one person is talking, the other is listening. When the one talking is done, the other listening can start talking and the one talking before can listen. So there are some rules that we follow. So the protocol is the same for two computers. It's a set of rules that tells them how to greet each other in the morning, how to then communicate, and how to deal with errors in case there's a communication error. So if I'm talking to a human being, they say something I don't understand, I might say, I'm sorry, I don't understand. Can you repeat that? Same thing with a computer. If there's a transmission, one sends to the other and the other doesn't receive it completely, it might say, hey, I think some bits are missing. Can you resend? So all of the how to communicate is handled by a protocol. So because computers can do different types of communication, there are different protocols for different types of communication. So for example, when I was using my web browser to search for images, I was typing a URL into my web browser. That idea of typing a URL and receiving a response as a web page is governed by a protocol called HTTP, Hypertext Transfer Protocol. So this HTTP is the protocol that we use for viewing web pages from web servers. But my computer is also connected to my home network in order to provide me connection to the internet. That connection is done using a different protocol, TCP/IP, Transmission Control and Internet Protocol. Then there are many other protocols for connecting hardware devices, like SATA is a typical protocol used to allow your motherboard to communicate with your hard drive. XML, RSS, and SIP are protocols for what we call transmission feeds. So basically, a protocol is just a set of rules that governs communication. If you don't follow any of the rules, you will not be able to communicate. If you fail to follow any of the rules, communication will not happen. Another key term we need to understand, and this is the last, I'm sure everybody's tired by now. This is the last thing we're doing today, standards. What is a standard? A standard can be defined as an agreed upon method of doing something. Early in the days of computer development, many companies were building computers, and the building of computers, everybody was building computers differently. I want you to imagine, in order to explain why that is relevant, I'm going to give you an analogy. I'm going to Google a picture of cars on the road. So the image that it's going to show, let me use this image. Now, here in this picture, you can see cars made by different manufacturers. This looks like a Subaru. This is a Mercedes. I don't know if this is a Honda or a Chevrolet. This is an Acura. Different companies making different vehicles. Now, in the class of vehicles, you have your coupes, your sedans, your crossovers, your Jeeps, your trucks, your buses, your lorries, your tractors, and so on. Different styles of cars. But all these cars, no matter how different and no matter who manufactured them, they have certain characteristics that are similar. Did you notice that all of the cars, despite their different shape, size, weight, length, height, they're all using the same type of road? This is because earlier on, when cars were being manufactured by different companies, the countries and the cities figured, okay, cars need roads, but we cannot design special roads for everybody's different type of car. So we have to have a uniform platform, a uniform definition of a road. So all roads around the entire world will have a specific width. It can be less, it can be more. And you as a car manufacturer has to build your car to work within those lanes. When you're creating a turn, there is a maximum angle that a road can take. When you're developing an incline like a bridge, the height cannot be, the incline cannot be more than 45 degrees. More than 45 degrees, the car's engine has to work at high rate in order to be able to make the climb. So most cars won't be able to climb something above a 45-degree incline. It will stall. So the car manufacturers had to develop standards, which were then discussed with the city, which was used to produce the infrastructure of the roads. So now, if you decide you're going to build your car and you're not going to follow the standard template of car manufacture, then you will build a car that cannot operate on a road. Let me show you what I mean. I'm now going to open up a new tab and Google the fastest land vehicle. The fastest land vehicle. That's this thing that looks like a spaceship. So you can see how long it is. This car, it's a car technically, but obviously it's not going to function on a road because it's too long to make those tight turns. Do you see what I'm saying? Is this clear to everybody what a standard is? A standard is when a group of people get together to agree on a set of principles on how to design and develop things. So in the world of computers, we have standards like ports. You have the USB port. So imagine I have an Apple computer. Once upon a time, not so long ago, if I wanted a printer, I would also have to go and buy an Apple printer because only the Apple printer can talk to the Apple computer. But by having standards, we can now have Apple implement a standard like USB. So if a printer manufacturer like HP builds a HP compliant printer, then I can use that HP compliant printer on any other USB, if HP builds a USB compliant printer, then I can use HP's printer on any USB compliant device. Can I get a thumbs up if that makes sense? So this is what a standard is. Now, a standard is not a must, you must implement it. But if you do, then all devices that follow that standard will also be able to work. So you will have interoperability and compatibility between devices made by different manufacturers, which is always a good thing. So examples of these standards can be seen in different formats. These standards, remember, I said it's an agreed upon method by a group. Though that group can be a committee, it might be a government, or it can just be a standard by what we call de facto. De facto is just people got used to it and then it became a standard. It's not that any single group of people sat down and agreed. It's just that somebody woke up one day and said, I want to build something, and noticed that around the world, everybody was using a particular format. Then they say, all right, that's now the new standard. So let's take a look at examples of standards. In computer programming languages, Java is a standard. Java can run on virtually everything. In fact, you can even run Java on your Wi-Fi router. Last week, I saw a video where a guy installed Doom. Doom is a computer game. Was it Doom he installed? Yeah, I think it was Doom. He installed Doom on his Wi-Fi router. So if you go to the Wi-Fi routers page, you'd basically be able to play Doom. So programming languages like Java, SQL, structured query language, and C and JavaScript are all programming language standards. They run on virtually every type of device. Examples of standard displays. The display is the technology or the format in which a screen can generate an image. So the MPEGs, the MP4, particularly the JPEGs and the GIF, these are all standard image or display formats. In other words, these are the formats that all screens can display, if, of course, they implement those standards. Character sets. How does your computer translate what your keyboard presses are? So you can have the ASCII, the Unicode, or the EBCDIC. So we'll talk about this in next week's lesson on the data representation. But just understand that the character sets are basically the keys on your keyboard. They're also standards. They generate a particular signal. In other words, this is why I can use any sort of keyboard on any device, because most of them will use ASCII or Unicode. Most computers now are Unicode. Then for multimedia standards, that involves multimedia, can be video, sound, picture, and so on. You can see a couple of examples here. So MP3 is by far the most popular audio standard, audio format. So these are standards. So what this means is these standards, you don't have to have them in your computer, but you can incorporate them in your computer. And when you incorporate them, it means you will have interoperability. So a standard can refer to a piece of hardware, a computer language, a display and image format, or a port. It can refer to anything. In fact, in APU, we have a dress code standard. That's the type of clothes that you can wear. It's a standard. We have a standard language. Everything in APU is in English. So your exams, the forms you fill out for admin, anything, any formal thing you want to do in this university, the standard form of communication is English. So does that make sense to everybody? Whereas when you look at a protocol is a set of rules for communication. It's different from a standard. Protocols are only for communication. Standards are for everything. Can a protocol be a standard? Yes. Is a standard a protocol? No. A standard can be anything. Just group of people agree to do a particular thing in a particular way. It can be design a hardware in a particular way. It can be design a software in a particular way. It can be format data in a particular way. It can be exchange data using a particular protocol or whatever. All of those can be standards. But protocols are only for communication, which means they govern the rules of how computers would communicate. So I'll give you an example. Bluetooth. Is it a standard or a protocol? Bluetooth. Is it a standard or a protocol? You can respond in the chat area. So I see somebody saying protocol, protocol, protocol. Now, the truth is, it's both. It is a protocol and it is a standard. What makes it a protocol? It's a protocol because it's a form of communication. What makes it a standard? It's a standard because it's an agreed upon and universally implemented. So in other words, if my Apple computer has Bluetooth and I have a Bluetooth speaker or a Bluetooth headbud or a TV or something else that has Bluetooth, I can connect the two and I can play out sound. Or if it's one computer to another computer, I can even transfer files. But you see, the Apple computers particularly, they not only have Bluetooth, they have something they call AirDrop. So this AirDrop is actually Apple's version of Bluetooth. It has Bluetooth already, but they also have AirDrop. AirDrop is a type of Bluetooth, but it's a type of Bluetooth that is special to only Apple devices. So the AirPlay or the AirDrop is Bluetooth, but it is only a protocol. It's not a standard. Why is it not a standard? Because it's not universal. Other devices can't use it. This is proprietary technology. Only Apple devices have this. So what is Bluetooth? Bluetooth is a standard and a protocol. It's a protocol because it governs communication, and it is a standard because it can run and it can interoperate between different devices that use that standard. AirDrop is Bluetooth, but it's not a standard. It's a special formulated type of Bluetooth. Bluetooth is just referring to a radio frequency range. So the AirDrop is a protocol that is not a standard. So that's basically it. So lastly, I have some homework for you. There's a video. I'm going to link the video in your channel, in one of your channels, for extra viewing. Now, this, I highly recommend you watch it. It's not absolutely compulsory. There's nothing inside the video that is going to be coming out in your exam, but I can't give you a long history lesson on the history of computers, so it's better to watch. So you can go search for this video documentary called BBC Shock and Awe, The Story of Electricity. It's 6 hours, by the way. It's 3 parts. Every part is 2 hours. It talks about the history from the invention of electricity all the way to digital equipment. So again, like I said, it's not compulsory, but it's a good idea to watch it. It's very interesting. I will be linking a shorter version of a history of computers in one of your channels. So in your channel, on your Teams page here, I will create a new channel down here for extra viewing. So I'll be linking videos for you to actually be watching. So before we go, there's this von Neumann architecture that I want to talk about. This is the last thing we're going to be discussing. So the von Neumann architecture is the general architecture of modern day computing systems right now. So if you look at this, this looks very similar to the input process output model that we saw, the IPO model. You can see here the control unit and the arithmetic logic unit are all part of the CPU. These two guys are part of the CPU. Then you have the RAM, the memory, and then you have the input and the output devices. So this is called the von Neumann architecture. And the von Neumann architecture is also known as the stored program concept or the stored program architecture. What does it mean? It's very simple. Once upon a time, computers used to be like this guy. Do you remember the Nintendo Entertainment System? You guys here in Asia would have known it as the Famicom. So this is NES. This is what the American version looks like. So people from Middle East, Africa, and the West, you would have recognized this. For people in Asia, it's called the Famicom. So the family computer looks like this. It's exactly the same device, by the way. They just look different, but it's the same hardware, same capabilities. Now, this is a computer. It's an 8-bit computer. And you can see here in this image, you can see it has an input device, which is the controller. This is the actual unit, and then it has cartridges. These cartridges are the computer programs that run on this device. So the way this computer works is if you want to run any application, which basically means you want to play a game, you have to take the cartridge by hand and load it into the device. Once it's loaded, then you turn the device on, then it can start running the application on the cartridge that you've inserted. This used to be how computers used to be. So the first computer I personally ever encountered is called the Commodore 64. So the Commodore 64 looks like this. It's essentially just a gigantic keyboard that you connect to your TV, because computers used to be so expensive then. So connecting it to your TV made the bill cheaper. On the side here, there are some ports and connectors, and it also has an input. So here you can see in this image, it has a disk drive here. So this is a disk slot for input. It also has a tape drive. So here's a better picture with all the components, so you can see it. So it comes with a power adapter, a tape drive, and this. The first game I ever played on this was the Ninja Gaiden. So Ninja Gaiden was on a cassette. What does a cassette look like? It looks like this. So a cassette tape. This. So the games used to come on these magnetic magnetic tapes. So this magnetic tape, you would load it into this tape player, and then the computer on the screen will tell you, please press play to load the game. So just like your PlayStation is loading a level, you press play. So it begins to read the tape, it loads the level. When it finishes, it stops the tape. Then you play one stage. When you finish, the screen says again, please press play. So you manually press play. So once upon a time, computers didn't have operating systems. You used to have to manually load things. The Commodore 64 has a rudimentary operating system, but the Nintendo Entertainment System does not. So the NES does not have, it's just you plug it, you put it and play. So the stored program concept was developed by this guy called John von Neumann. And he was the guy who says, instead of having cartridges, why not we have a permanent storage unit that can hold the applications, and anytime we want to run them, the computer can just run it. And that's why I now have installed programs on my computer. It's by the development of this John von Neumann. So before computers didn't have the storage used to be external. So he says, why not we incorporate the storage into the computer and then have a stored program? So that's the stored program concept. So when we want to run the application, we load it onto memory from our hard drive. So rather than manually installing it on a cartridge or on a disk, we simply load it on memory. And whilst it's on memory, we can run it till our heart's content. And that's that for today. I believe I've covered everything. So the rest is history, which I mentioned. I will be sharing whatchamacallit. So for those who came late, here's the attendance. So before you go, please make sure that the attendance has been scanned. Now, if you have any questions, you can go ahead and type them. And I can see if I can quickly address them, although we are out of time already. So I have 20 people absent. So people keep asking me, am I a fan of Naruto? Yes. Isn't that obvious? All right. So I don't see any questions coming in except attendance issues. So I'll go ahead and stop the recording at this point. And next week, we will be entering the topic of data representation.